All right. So we're going to talk about something called Ampere's law. It's going to be another law with a name, but it's quite related to what we did before with the right-hand rule and the forces acting on a current and things like that. But this time, it's not that a current in an electric field will feel a force. This time is a little bit different. This time, a current will create a magnetic field. Okay, so that's another thing that we haven't looked at yet. Before it was what happens when you put a current in a magnetic field. Now we realize, holy crap, currents are actually producing magnetic fields, and we didn't know about it. So that's the basis of what's going on today. So an electric current in a wire produces a magnetic field, and the way to figure out the direction of it, guess what? How do you find the direction of the magnetic field? Right hand rule. Okay. Um, you can use your left hand rule if you go in the opposite direction, if you're considering that it's electrons moving. So just always remember, if you're considering electron movement, use your left hand. If you're considering proton movement, use your right hand. Both will give you the right answer regardless. Okay. So let's figure it out. So here I have a wire that has a current I. And if you wrap your right hand around it, your fingers, the way they wrap, will indicate the direction of the magnetic field being created. All right, so in this case, it would be like this. All right, so there'd be a magnetic field going around the wire like that. Okay? And because it's a wire is let's say a very long cylinder, the magnetic field created around it is going to also be shaped that way. It's also going to be circular around. So if you look at this cross section here, the magnetic field is going to be a circle, right? And the strength of the magnetic field is going to depend on how far you are away from the source. So R here is very important. Does that mean that there's only a magnetic field at this distance R? No, it doesn't. It means that it's a function of R, which means that it's everywhere, right outside the wire. So the magnetic field strength is going to get is it going to get from strong to weak or weak to strong according to this relationship here? You can't see it? No. You want to come sit here or something? No. So R is in the denominator. Does that mean that the close ones will generate a strong magnetic field? Or when you're far, you're going to see a strong magnetic field? Closer, exactly. So the closer you are to the source of the current, the stronger the magnetic field is. The stronger the current is, also the stronger the magnetic field is. So the current I is going to be in the numerator, and the radius R is going to be in the denominator. Those are really the only two variables. Everything else is pretty much a constant. And now we have this new one here. This is called permeability of vacuum. Okay? Permeability. Or it's actually called vacuum permeability. That is all that correctly. Vacuum permeability. Gosh. Okay. It's confusing because we also have permittivity and permeability. I don't know how they name these things. Okay, and that's the constant mu naught, and then 2 pi. Those are also. So really, the magnetic field depends only on two things. It depends on the current, so how strong the current is, and how far away from the current you're sampling the magnetic field. Because it's cylindrical around, you can have instantaneous magnetic fields, right? So if I were to just take one of these points along, at this point here, the magnetic field would be going in that direction. At this point here, the magnetic field is going in the down direction. And so depending on where you look at along the wire, it's going to look differently. So if I have a wire here like this with a current going in this direction, all right, what is the magnetic field going to look like in two dimension? What is the magnetic field going to look like on top of the wire and below the wire? So use your right hand and figure out what your fingers are doing. Don't have an answer? Yeah? Where? On the wire, on top of the wire or below the wire? So below the wire, you say they go in which direction? Down, okay. Maybe don't write this. Let's see if we have other answers. So on top of the wire, they go up. You all agree with this? Always down, regardless of if it's up or down. Any other answers? Question is, if I were to draw the magnetic field on my two-dimensional drawing here, which direction would the magnetic field be pointing, on top of the wire and below the wire? That would be me drawing it in 3 dimensions. I want to take a cross section, drawing it in only in 2 dimensions and considering only on top of the wire and only the bottom of the wire. Okay, so there's another answer. So where is it coming towards you and where is it going away from you? So this is another answer that we got. Away from us at the bottom. Okay, anyone else have an answer? No? Okay, so one of these is the right one. Which one? Yours is the right one. Okay, so we have to use our right hand rule and let's figure out. Right? So we have a wire going towards the right. Or current. My fingers are going towards the board, down or what? Right now, what about you? My fingers are underneath the wire. So here's the wire, right? My thumb is in that direction. What are my fingers doing underneath it? Towards the what? Towards the board, which is away from you, right? And if I go all the way around, same hand and everything, what are my fingers now doing when it's on top of the wire? Towards you there, okay? Sorry, Mark, break you the news. The answer is that it's this. Okay? So this is your current I. This is your magnetic field B. Okay. And if I were to ask you, what does it look like in front of the wire? So you have the wire like this. You have the wire like this. What would the magnetic field be right here? Right here. Not a circle. The instantaneous magnetic field. Straight down. So let's try to figure that out. Yeah, absolutely. Right. So if you wrap your fingers around, your fingers would be going downwards on right in front. Yeah. Okay. Okay. Good. But that would be in front of the wire, not on top or below the wire. Okay, perfect. Questions about this? All right. Let's see if you can answer this question for me. I have a loop that has a current going through it. I don't know the direction of that current, but I know the magnetic field direction. So which direction would my currents be going? Let's see them right hands. Which way? From the top towards the bottom? Okay, like this. Okay. Does everyone agree? So Melanie agrees. Everyone else disagrees? You agree? Okay, good. Thank you. So everyone else disagrees? Now we're at 13 students, 14 students left who need to agree to this. You guys are so awkward. Okay, so yes, absolutely. The answer is correct. And there is a magnetic field inside. This is super important because we're going to use this concept now for the next part of the course. Now, inside this loop, there is a magnetic field, and everywhere inside that loop is pointing in the same direction, right? So that's similar as if I were to have just a magnet, the north pointing up, the south pointing down. This is exactly the same thing. So what I'm doing now is if I create a loop with a wire and I run a current through it, I'm creating a bar magnet with a north pole and a south pole. All right? Because look, if I had a magnet in there, it would be doing the same thing, right? If I were to draw my magnetic field lines, wouldn't they look like that? They would look exactly like that, exactly. So that's what I'm essentially doing. By creating a loop with a current running through it, I'm creating a magnet. So this is termed, what is this called? You might see this really powerful ones in like a trash compactor. They're called electro, oh boy, electromagnets. Yeah, exactly, electromagnets. Any questions on this? Yeah, yeah, sure. So if I have a current, this is going to go upwards instead of pointing in that direction, and my fingers are wrapping on the outside of the wire. So if this was like the instantaneous current at that point, then I need my magnetic field lines to be going that way, and therefore my thumb can only really be pointing in that direction. So here instantaneously, my current is going towards the left. So it looks like this. Okay. So that's the instantaneous current in that direction. Here, the loop is, the wire is coming up this way. And so if I wrapped my fingers, it would be going through the wire, which is exactly what that picture is showing. Right? So at this point, my current would be going this way. And then here, you can see that the lines are going behind the wire, right? So that means it's going behind. Something like that. Okay. So this is exactly like an electromagnet. This is an electromagnet. Uh, Electromagnet, and behaves like a permanent bar magnet. And so I can magnetize things with this. Remember how I told you that you can pick up a paper clip and that paper clip can pick up another paper clip? That's because we were magnetizing one thing and that thing is going to magnetize the next thing. And originally we said that we can do that with permanent magnets. But that's actually not true. We can actually do that with electromagnets as well. Okay, okay, so what I want you guys to do real quick is to draw for me the magnetic field lines on these diagrams, the direction of them. So the right-handed rule thing applies here. So hopefully for the first one, ooh, you got something like this. Keep going for the others. For the second one, hopefully you got something like this. Which one? This one here? It depends on where you're sampling it, right? So if you really want to be picky about it, it could look kind of like this. It's really just saying the same thing. Yeah, yeah. Oh, uh, that was right here. It's just difficult to imagine because it's not in 3D. It's a 2D drawing representing a 3D situation. So at that point, the point that I just drew there on the left here, the wire is coming towards you, right? And so it has to the you have to use a right hand rule, and then you have to draw the thing. So on here, or anywhere actually here, the magnetic field is there. Here the magnetic field is upwards. Here the magnetic field is downwards. Here the magnetic field is that way. It's never just in one direction. It's always circular when it's a current. All right, so for C, I'm going to have a hard time with this one. The marker's not working. Oh, you. No, okay. All right. So for D, it should be the opposite of B, like that. And this one is going to be round like this. Like that. Just going to ask you to make sure that we all understand everything. For figure E, the way I drew it, which location relative to the wire is the magnetic field pointing upward? So according to this wire, we're talking about letter E, all right? Relative to this one, to this wire here, where is the magnetic field pointing upward? At the top? Anyone else? You? In front? We got one wrong answer for sure because there's two different answers. Underneath? Underneath. Okay, so now we have two wrong answers and one right answer. It's, if I were to look at it right in front here, what's the instantaneous vector for the magnetic field? This is in front of the wire. Instantaneously, which way is the, if you had to draw a tangent, for example, to this curve, which direction would it be pointing? Upwards. Yeah, absolutely. Right. So this is an up at the front of the wire. There is an upwards magnetic field. Okay. Okay, let's do the opposite now. Now we know the magnetic field. Let's try to figure out which direction the current is going. The first one should be pretty straightforward. You guys get it? What'd you get? Point, exactly, or towards you. And B, I'm gonna call this left here, and this is gonna be right. So is it going towards the left or going towards the right? Which one? Oh, oops, sorry. Toward this end here? Yeah, exactly. Okay. Is it? I still disagree. Hold on, maybe I'm playing mind tricks with it. Oh, you're right. Yeah. And the last one? Towards the right. Okay. So this is the direction of current. Okay. So obviously we have to think about how this affects modern technology and all that stuff. We'll turn a circuit and see what happens, because in all circuits there is a current, right? And we need to understand that all our currents and all our circuits, there's a magnetic field being produced. So hold on. We said that right now we're in a space of a gravitational field, because everything we do feels a gravitational pull. We have all sorts of charged particles all around us, especially the charged devices. That means there's electric fields everywhere. And now I'm telling you that everywhere that there's a current, there's also a magnetic field. So right now, really, we're just in a space of different fields, of different kind of physical phenomenon happening at the same time. Some might think that this is why we're unhealthy. These are conspiracy people. Like obviously, there is no truth to this, but that we're always in a location where there's some kind of field. It doesn't have any effect on our body as far as medicine is concerned. All right, the fact that we're in a strong magnetic field, strong electric field, strong gravitational field doesn't have a negative impact or positive. Yeah. No, those are radio waves, and radio waves are very low energy waves. Yeah. In fact, they're the lowest energy waves. Yeah. If you were next to an X-ray machine or underneath one, maybe not. Okay, so let's talk about circuits. So the capacitor in this figure is charged to 50 volts. The switch closes at t equals 0 seconds. Draw a graph showing the magnetic field strength as a function of time at the position where the dot is indicated. On your graph, indicate the maximum field strength and provide the appropriate numerical scale on the horizontal. So hold on. Okay, this is complicated because we're talking about RC circuits now, right? Because I have a resistor, I have a capacitor. And so what can you tell me about current when I'm discharging? Does the current increase or does the current decrease? The test is in 2 days. Everyone should know this. The current will decrease, exactly. So if the current is decreasing, this here is going to feel a magnetic field that's going to be decreasing or increasing. Decreasing, exactly, because it's totally proportional to your magnetic field, to your current. All right, so if the current is decreasing, then the magnetic field is decreasing. All right, so let's figure out an expression for the current. So we said that current is a function of time. Do you guys remember this, or maybe doing some exercises in preparation for Friday? What's that? Yeah. That would be if it's increasing. So you're close though. It's not the one minus, it's the other one. Yep. E to the power of negative t over or tau or RC or whatever you want to call it. All right, so that's how we express current through this circuit. All right. And if I were to determine what the magnetic field is in this current, well, what's the relationship between current and magnetic field? Well, that's pretty simple, right? We can just talk about magnetic field being a function of mu naught times current over 2 pi r. And this r here at this point now is constant, right? So actually I can just multiply that on either side of my equation and it should be a-okay. So I can say that mu naught of this function over 2 pi r is going to be equal to mu naught I naught over 2 pi r multiplied by e power of minus t over tau. Okay, so at any point in time, I can determine what the magnetic field is. So this is going to be magnetic field as a function of time is going to be equal to the initial magnetic field at that point there, right, multiplied by e to the power of minus t over tau. So the strength of the magnetic field would follow the same kind of curve as current. So what would be the maximum that this can have? Well, that would be pretty easy to calculate. It would be this value here. This is going to be your maximum magnetic field. It's going to be at its maximum when it's at its time is equal to 0 state. So I don't remember what this constant is. I'm just going to go back and look at it. 4 pi times 10 to the minus 7. So B is equal to 4 pi times 10 to the minus 7 multiplied by the initial current, which we can figure out in a second, divided by 2 pi times r, which is 0.01 meters. And so how do we know what the current is, the initial current? The voltage across my capacitor, 50, and I have my resistance. Which law may I use? Ohm's law, exactly. So now let's figure out the current, the initial current. It would be 50 volts is equal to 5 ohms multiplied by I. So I is 10, and I can replace that in here. Times 1,000. This cancels each other out. So 2 times 10 to the minus 4. So what you guys got? Yeah? Units? That's units. And so this value here is going to be V naught, which we just calculated. That's the maximum magnetic field, the initial magnetic field. Yep. Yeah, it should, as my drawing is bad. Yeah. And it should not touch the bottom, actually. It's on here. So far, so good? All right. So here I have 2 wires now. All right. And magnetic field is a vector like any other vector. When you have 2 vectors in the same spot, what do you do with those vectors? Yeah, exactly. You add it. Okay. So I have 2 wires here, and there at each point, 1, 2, and 3, there's going to be 2 vectors that you're going to have to add together in order to find the resultant one. At point 1, right? So I'm going to go up to the board. At point 1, I have a magnetic field that's coming in which direction? Out of the page. That's due from the first one. And this one here is going to be into the page. Who's going to win? Which one's going to have a stronger magnetic field? This one or this one for point 1? Why? They both have 10 amps, so the current is the same. What's the other thing that matters? Current and R, exactly. So which one's closer to the point one? This one here. So if this one's closer, then this one's going to win the magnetic field fight. Let's call it whatever you want to call it. So like here, I'm going to have a field going in, and here I'm going to have a field coming out. Which one's going to win? Which one's going to be the resultant direction? Coming out or going in? At this point. Out. Okay, this one's going to win because it's closer. They have the same current. This one's going to have a stronger magnetic field here because it's closer. And that one produces a magnetic field coming out. And you can figure out the mathematics by just applying the formula. Yeah, you would have to do that. So in this case, for point one, you would have, I'll just write down the equation. Mu naught times 10 amps divided by 2 times pi times, what's the distance from the first wire? Yeah. And this would be minus, because it's going in the opposite direction, right? For the next one, which is mu naught times 10 amps over 2 pi multiplied by, and what's the distance in the second wire? 0.06. And that gives you some number. I'm not going to calculate it, but that's how you do it. The direction would be outward. What about at point 2? Nothing happens? You sure? Chances are. Give you a hint. I haven't found the right answer yet. Yeah, what do you think? They add up, right? Because look, before one was above both of the wires, but now one of them is below one of the wires and above the other one. If you use the right-hand rule, right? So for the first wire, for the first wire here, the top one, the magnetic field is going to be going into the page. If you use your right hand, right? And for this one, if you're going towards, come on, if you're going towards the left, then it's also going into the page. So the vectors actually add up. So you're getting double the magnetic field strength going into the page at that point, right? So if you want to find the magnetic field at point 2, it would be that B is equal to 2 times whatever you end up doing for one of them. So 2 times mu naught times 10 amps over 2 pi times 0. What's the distance? 0.02, exactly. It's halfway between each one. Okay, Mark, you had a question? Okay. Like in that case, would like point 2? You're correct. If they were going in the same direction and you took a point midway between them, then there would be no magnetic field. Okay. And so this one at the bottom is the same as the first one, except in the opposite direction. So far, so good. It's really all about using your right hand and not getting lost in the 3D space of this 2D image. I find that to be the hardest part. Okay, this is important. Not important, this is interesting, all right? So let's say I have a wire, and this wire has a current I in that direction. And show me this in this drawing here. I want you to show me below the wire, what is the magnetic field going to look like? Use your right hand, tell me for my lone wire, which direction the magnetic field is going to be. Towards the board. So this is going to produce a magnetic field that looks like this. Pretty much everywhere below the wire. It's going to get weaker and weaker as you get further and further away. But essentially, it's a magnetic field everywhere down here. Now, that's all due to this one wire. Okay? If I had another wire here going in this direction, I'm going to call this another current I. Call this current I prime. All right? Now, what we have is a current in a magnetic field. So what can you say about a current in a magnetic field? We learned this last class. When you have a moving charge or a current in a magnetic field, it feels a force. Exactly. So that means there's a force acting on this other wire because this is another wire in a magnetic field. So how do we find the direction of that force? Well, let's use our right hands again. So thumb to the right, fingers into the board. Palm is in which direction? Up. So this thing here, this wire is actually going to feel an attractive force to the other wire. That's kind of cool because there's just two currents and then they're being attracted to each other. What if the currents are opposing each other? Then which direction would the force be? It would be a repulsive force. So if the currents are going in opposite directions, then there would be a repulsive force because one's producing a magnetic field for the other, and that one's going to feel a magnetic field and has a moving charge, and therefore it's going to. So now, but also, hold on, don't forget that this wire is also producing a magnetic field all over here. So that one's also going to feel a force. Actually, I drew my magnetic field on. Did I? Yeah, I drew it wrong. It's going to be circles. And so what's going to happen to that wire? It's going to get attracted or repulsed. So thumb to the right, fingers outwards, thumb to the right, fingers outwards. That would be palm which direction? Down. So it would also be an attractive force. So the two wires will attract each other. And there's a pretty neat experiment. I mean, I could show you a video on it, but it's incredibly boring and hard to see. But it really just shows that. So you have two running wires next to each other with the current running in the same direction, and they attract each other. So if you want to have a trick to remember, you can remember that like currents attract. It's opposite of charges. Opposite charges attract, but like currents attract. Anyway. And you can quantify that force between the two wires. There it is right there, right? This D represents the distance between the wires. This represents each current. This represents the length of the wire that overlap. What's that? It's the length of wire that overlaps. So it's, let's say this wire is this long and this wire is this long. Well, they only overlap for that amount. So that's the part where they're gonna. That's your L right there. And of course, this is just the magnitude. Let's put that into practice here and do this. I'll let you guys work on it. What answer did you guys get for I2? I know, but I want to figure out what's the current in that circuit. 3? What I got? Is this okay with you guys? Is that what I did? Okay, let's take a break. We already done this. So. Come back in 10 minutes. Yeah. Oh, okay. Yeah, sure. So where's the equation?
Right here, because I found the vote, but then we wanted to ask what was the
Okay, so
time when
let's
it
set
could
this
pass
up.
the time.
Do you mind if we go on the board?
Yeah.
Let's do it on paper. Okay, so here we have you're trying to solve t here, right? Negative 0.66. I'm assuming all this is correct, but it doesn't really matter. Is equal to 2.71 minus t over. Isn't there an e in here somewhere?
Well, the E I already read it. It's 270.
Okay, let's leave it as e because that's going to be important. Okay. So in order to do that, what you need to do is remember your exponential and logarithm log. So that thing. Exactly. So if you can do the ln on both sides, so the ln on both sides would be this. And when you ln this side, it's just going to equal to this minus t divided by 282. So that brings it down, right? And now you can do that. So it'll be 282 or minus 282 multiplied by ln of 0.66 minus 0.66. It's going to be equal to 2. Okay.
And I have
Yeah.
I don't get what origin take.
All the ones that are involved in that part of the circuit. All right, so is this when S1 is closed and S2 is closed? Or
S1 is closed, open, and S2 is
S1,
open, S2.
so it's just this here?
Yeah, but I had a question from one as well.
Okay, hold on, let me answer first.
Yeah.
Okay, so let's say it's just this part of the circuit.
So do you think that our S1 is open and S2 is closed?
Yeah, if that's the case, then really there's only going to be current in this region here. And therefore, that's the only R that you consider, and that's the only C that you consider. If this switch was open and this switch was closed, then it would be this, and it would be this, and this would be in series, right? So you just have to like just imagine if this is not gonna exist if that switch is open. Okay, so if S1 is closed and S2 is open, then it's really just this, and this is going to be your C, and that's going to be your R.
It's right here.
Yep.
Okay. The amount of trouble with this is that makes
Okay, so steady state doesn't matter. You don't have to. Steady state is two things. One is when the primary most important thing that steady state is when the capacitor is full. I'm not asking you about anything about time or anything like that. The 5 RC thing that you're talking about, that's the amount of time it takes to reach steady state. But that's not what it's asking you here. Now it's just asking you what happens at steady state. And at steady state is this capacitor is full. So you have to find the voltage on that, right? And yeah, exactly. It's going to be capacitance.
Okay. That's why I was wondering, because I know the amplitude is from here.
Yeah, it's not times 5 is really the amount of time it takes to reach steady state. So you multiply your RC times 5, and that much time is what it takes to get to steady state. Right.
So there's this circuit here.
Okay.
And then it says the value of resistor R2.
You have to use this graph.
Yeah, I know, but
So this graph tells you that at steady state, right, it's 12 volts, right? So that means there's 12 volts here, but because it's in parallel with this resistor, that resistor is also 12 volts. Yes, so remember that when you have parts of the circuit in parallel, they're going to be the same voltage outputs. Okay, so that's 12 volts, then that means this is 12 volts, and that means this is going to have a current, you're going to have V divided by the resistance. Exactly. And because this and this are now in series, remember this is fully charged now, and therefore doesn't exist in the circuit. So the current that you have there is going to be the same current you have there. Right? And if you have the voltage there, the difference of voltage is going to be that, yeah, it's really not that hard, yeah. So 20 minus 12 is going to give you 8 volts for that, and whatever current you have there is going to be the same current for that, and therefore you can find your resistance. Exactly, yeah. The 12, right? So the max here, so the capacitor voltage reaches the maximum voltage of 12. So therefore, at its capacity, this is going to have 12 volts potential. So that would be the V that you would use. 12 squared multiplied by the capacitance divided by 2. Okay.
Yeah, but
Are you being classist? Are you being classist? Yeah. So les gens de Brébeuf sont genre. That's classist.
I will not answer the rest. I will finish my sentence.
I used to teach at a school called Miss Edgar's in the cram school, and the tuition there was like $20,000. Crazy. type of family.
It's actually like cheaper than St. Pat's.
I guess.
But I mean, I can tell like go there, it's like yeah, well, it's, you know, no filter, but it's cheap. I mean, like yeah.
I
It's
remember,
very superficial. Like
I'll never forget this. I was at the office at my old school, and a girl who was in grade 6 forgot her homework at home. Oh no, sorry, forgot her lunch at home. And she's calling her mom, could you bring it? Oh, I'm sorry, I'm working, whatever. And then she's like, what do you mean you're working? Can't you just get the chauffeur to bring it for me? I will never know what that's like. Oh, uh-huh. Yeah. And sometimes they like they're humble. Yeah, sometimes they're humble. Everyone has got one person in mind.
my friend asked what time it is. And he's like, well, it's time to buy your watch. But then he shows up his watch in such a disgusting manner. He's like, certainly not like a Rolex, you know? And I'm like,
Wow. How old is this guy?
I think it's like 17.
Ah, like when they're young, at least there's like an excuse, you know, they don't know yet.
Made like a fortune by inventing something or something.
Yeah,
It's not nice, but it's understandable. I mean, you want to show off.
yeah,
But you should base like who you are based on
yeah, absolutely.
who you are.
Wow, I can't believe that people are like that.
But I want my guy like went to St. Pat before.
Yep.
I was like, yeah, St. Pat, we need to teach for that. And I was like, I'm sorry, but actually it's better than yours in terms of the rankings.
You know, the school that's crazy. They're like first or second or like tied for first. Yeah, yeah. I was impressed a lot. Okay, let's get back to this. This second part is going to be quicker because it's really just the same concept. So I'm sure you guys remember the concept of solenoids back from high school. I mean, at least the term solenoid. You guys remember what it is, what it looks like? Nothing? Not even close? No? What is it? Yeah, it's like a spool of wire. That's exactly what it is, right? So imagine, remember we're talking about how a loop has a magnetic field. Well, imagine if you had many, 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 many loops, like if you had a wire that would literally spool hundreds of times around itself, how much of a magnetic field that would create. Okay, so let's figure that out. Here it is, picture of a solenoid. All right, and we saw that when you have one loop, there is a magnetic field being created, and if you have one loop like this, and there's a magnetic field going out that way, well, that means if you put another loop next to it, there would be another magnetic field going in that way. So are the magnetic fields coming out of each loop, are they adding up or are they canceling each other out? They're adding up, exactly. And if they're adding up, then you're creating a stronger bar magnet or a stronger electromagnet. Okay? So let's figure out what the relationship is between those numbers of loops and the magnetic field. It's going to turn out that the number of loops is actually quite important. More loops you have, stronger the magnetic field. All right. This is what it's going to look like. So again, all you're doing is you're amplifying the magnetic field and you're creating a really strong magnet, right? More loops, even stronger magnet. We've figured this out is if we want to figure out where the magnetic field is going, you can use your right hand again. So another right hand rule. The rule is in this course, if you have to use your hand, use your right hand, all right? Unless it says the term electron in the question. So if you're using your right hand here and you curl your fingers around the solenoid in the direction of the current, then the thumb is going to point towards where the magnetic field is going to come out of, right? And so here we have the strength of the magnetic field B from a solenoid. And this value n is what's really important. This is the number of loops. Number of loops. This is the strength of the current. And this is the length of the solenoid. Why is length in the denominator? I thought we said that the longer the wire is, the stronger the magnetic field is. Yeah. Exactly, right? So actually what's really important is not L on its own, it's N divided by L, right? So if we look at these two together, N divided by L, what is that? What can you call that? Give it a name. Not charge density, but I like density. I like density a lot. What kind of density? Loop density, exactly. How many loops per unit length do you have? More loops per unit length, stronger of an electromagnet that is. Okay? So we're gonna call this loop density. It's not really an official term, but it's just to help you understand what that means. Any questions on this? So here we go. We're going to try to figure out what happens if you have a loop inside of a current, or many loops inside of a current. Which direction is the magnetic field? Which direction is going to be the magnetic north? So in this case, the current is going up or down in the first one, starting from the battery. Which direction? Up, exactly. Right. So if the current is going up, it's going like this. So if you put your fingers to go along that, which direction is going to be the magnetic field? Is the current going towards the bottom of the bar of the solenoid or towards the top of the solenoid? What is up? Sure. At the bottom, exactly. So you have to see where the current is going. The current is going towards the bottom, and therefore the magnet's at the bottom. So it would be the opposite here. Hold on, do I have this? Yeah, sure, it would look like this. It would be like a magnet. Yeah. Like that. Okay. So the trick here is to follow where the current is going. Right. So in the first situation, the current is going downwards, down the solenoid. So would put your fingers down. Although it's kind of counterintuitive the way it's drawn. It's really hard to imagine these things in 2D. Okay, let's do it the other way around now. Now you have the magnet and you're trying to find the direction of the current. So put your thumb in the direction of the north and see which direction the current is going. So I would start here or start here. Which one would I choose? Yeah, exactly. You would start here. Go like that. Like that. Okay. And for B, which one does it start? On the left one or on the right one? Yeah. Oops. Trying to say that. Okay. I'm sorry? Start like what? So I mean, it's again hard to imagine with the two-dimensional drawing, but imagine that your fingers are following the loop of the wires, and therefore your thumb's going to be pointing towards the left. Right, so the current has to be going in that direction. If you find that you put your thumb in the left and your fingers don't follow the curvature of the wires, that means you're going in the wrong direction. Are you talking about the one on the left or the one on the right? Okay. So thumb is towards the right, right? So that's where the magnetic field is. You see the my fingers are going to wrap around the front part of the solenoid. And if I'm going to go behind, there, they're going behind. So that works for both. It works for behind and what's that? No. In this solenoids, your thumb is the direction of magnetic field. So I can make my electric field. Okay. Here's another one. This time it's asking you for the magnetic field inside and outside the solenoid. Use the X's and circles and that cross section. So imagine you took a solenoid and took a saw and you cut it directly right down the middle, and you're seeing the cross section of each of those wires, and it's telling you the top row is it coming out or into the board. Out or into the board for the top part. Here. What does that symbol mean? Coming out, going in, coming out, coming towards you, right? All right, and this one is going away from you. So that means that at the top it's going to look like this. At the bottom is going to look like this. So therefore, the electric field on the inside is going to be how? At point I, the magnetic field is going to be towards the right. And it curls around, comes back this way. Like that. Now the question asks, what happens if you were to put a compass? With a compass, where does it point to? Okay? It points towards the magnetic south, exactly. So if I put a compass here, it's going to point towards that. This would be, so remember that magnetic field lines go like this, north to south. So this is the north, and it would be pointing this way. If I had one here, it would be pointing that way. Easiest way to remember what a compass does is it does what the magnetic field does. Okay, if the magnetic field is going up, then the compass is going to be pointing up. If the magnetic field is pointing south, then it's pointing south. Yeah. Yeah. Because a compass tells us where the geographic north is. That's why it's this. We're no longer talking about the geographic location because we're creating an artificial magnetic field. All right, next example. A solenoid used to produce a magnetic field for research purposes is 2 meters long. Okay, perfect. There's our L. With an inner radius of 30 centimeters and 1,000 turns of wire. Right? Running a solenoid produces a field of 1 Tesla. Given this, how large a current does it carry? So we have V is equal to, I can't remember the equation. Mu NL over I. Multiplied by. Does the fact that I have a radius matter? No. The strength of the magnetic field is independent of the radius of my solenoid. Based on this, do you think the current's going to be really low or really high? Really high? Well, look, 1,000 turns, 2 meters in length, and I only got 1 Tesla. That's not a very high, current. Really high magnetic field. So I'm expecting actually something quite low. Yeah. Where do you see that? Oh, I don't know. I don't know why I wrote that. I was still thinking of the other relationship from before. So if you solve for I, maybe you are right. Maybe it is a high. I don't. 16,000. Okay, so I stand corrected. 15,000. How much? Does everyone get that? 1,600. 10,000. Okay, now everyone's getting different numbers. So let's try going back and everyone double check your calculations. Wow, I got nothing. I got none of those. That's what I got. Did you, when you guys did 4 pi times 10 to the minus 7, did you leave it as 4 pi times 10 to the minus 7? Because don't forget, you have to divide by 4, divided by pi, divided by 1 times 10 to the minus 7. I got what Anne Michelle got. Let me just try it again. 1 times 2 divided by 4 pi times 7 divided by 1,000. I got 1,591. Yep. So I stand corrected, very high current. Okay, next example. Is the magnet attracted or repelled by the solenoid, the way it's standing right now? If I were to look at my green solenoid, where is the north end of it? Or in fact, where are the magnetic field lines pointing to? right? I'm looking for which direction my magnetic field is pointing towards for my solenoid. Right towards the right. If my magnetic field line is pointing in this direction, that means this end is my north or my south. It's going to be my north because it's going from my north into the south. This is going to be north. It'll be attractive. So far, so good? This is exactly how a speaker works. All right, so you have a solenoid who's acting like an electromagnet inside your speaker. So if you guys, have you guys ever, or maybe not, if you ever taken apart a speaker, you'll notice that there's like a, kind of like a tampon, drum. Yeah, okay, so there's like a drum, the speaker that's moving the air up and down, moving up and down, moving up and down. That's this area here, this gray area here. And this, when it moves up and down, it vibrates the air and it makes sound. All right. So now you need to move this thing up and down and respond to current. So what you'll have is at the bottom of this membrane, the tampon, you'll have a magnet. It's a regular magnet, or circular magnet. And underneath it, you'll have a solenoid. All right. And the solenoid is going to have a current that passes through it as in a frequency or in the strength related to the sound that your speaker wants to produce. So like the computer or your iPod or whatever it is, it's going to send current in the wire to make the magnetic field stronger or less strong, right? And the fact that it's going to be stronger is going to pull the speaker part down, and then when it becomes weaker, it's going to let go of it and it's going to go back up. So the movement up and down of this magnet is going to cause movement in the air, right? So this thing here, this solenoid that you see here, is going to attract or repel the magnet that's located right there. And as it's attracting it and repelling it, that movement, that attraction and repelling, is associated with the movement of air molecules that's being produced by that speaker. It's actually very, very, very elegant the way it works. At the same time, super duper simple. If I were to have something like this, what would happen? So here I have a doorbell, right? Did you say it's a gong? Yeah. Well, I mean, that is what a doorbell is. It is kind of a gong. And basically you want this thing, this hammer, to kind of strike it, right? So what are you going to do? You're going to press this button, and that's a switch, and you have a circuit. And in a circuit, which direction is the current going? Positive to negative. So you're going to have a current going this way when you press the switch. Okay, so your switch is going to make the current go this way, this way, this way. It's going to make it's going to have a solenoid here and here. So therefore, you're going to have this kind of magnetic field line. And what's going to happen is you're going to polarize this bar here. This bar here is going to get polarized, and it's going to get attracted to it because a metal that's put next to a magnet is going to get attracted to the magnet, and therefore it's going to strike this bell. Right? Very simple, elegant design. Don't need anything very, very complicated to create something like that. Electromagnets are pretty cool. They're everywhere, everywhere, everywhere. I keep saying that about everything in this course, but because we're in an age where everything is basically electronic, electric, and magnetic, and everything. That's all I have for you guys for today. Any questions? Yeah. Okay. So, for the most part, it was really, really well done. Definitely above what my expectations were. The average was, I believe, for you guys, 72. Although one person did get a 0 uh, because they dropped out of the course, and so the real average is actually like 69 or something like that. But so don't let that deter you. All right, the average is actually a bit higher than that. It shouldn't count. Um, Most common mistakes, I mean, there wasn't really one really common mistake, but for sure, like a lot of you are forgetting about sig figs. especially on a lab test, that should be quite understood when you're talking about Sig Figs. Um, the mystery box was, well, some of you had to do a different one. So, I mean, they're well done. Most of you were able to get it. The only one thing that the mystery box that I couldn't understand why some of you did it. Some of you said that the batteries were in parallel. And the batteries aren't in parallel because it's set on the box. There was four 1.5 volt batteries for a total of 6 volts. That can only mean that they're in series. Um, and I didn't even think that that would be like a point of contention, whatever. Oh yeah, very common mistake. There was the station where you guys had to take a picture. Do you guys remember? You had to create a circuit, longevity, whatever. That was all good. Everyone did that one well. But the one right after that was the one where you had a bunch of resistors in parallel, and you had to find the most accurate way of measuring the resistance, right? The most accurate way of measuring resistance is a special way to do that. What is that way? What's it called? One person in this class. We filmed it. You could have, if you removed it and measured it, I gave you some marks, but you really did need to use it as a weak stone method way to get the points for that. All right, council question 10. That's the one where if you were in Tanya's room and things didn't work, it canceled it for everyone. Didn't even try. That was okay. Yeah, otherwise everything is good. All right, so you look at it, so take a look. Before you leave, just give it back to me, please. Is that something for like, wow. But that's not, you end up being like, no, the calculation is not. The answer is supposed to be 0. Yeah. I'll look it up. Then you're gonna really matter. You're amazing. If you can get your hands in I think I like that. You have to show me that there's a current going on. Yeah. You're way off 1.5 million. Not even close to zero. That's just zero. Put it in the computer. Open up the browser. Yeah, like they didn't do it correctly. If you're setting it too high, so what happens if you're setting
All of your settings were like, it doesn't work.
yeah, so then it was like
So I simple.
let's you put on the it would say 010 no matter what. That's what you zero 1 0 is not a real value. There should have been one that worked for everyone, right?
I don't know what I did.
Are you sure you were testing it?
I was like, yeah.
I have to show you how to work it.
I was the first of that station when somebody Why is it I'm not gonna test on it? Still be able to find. This
It's not matter, it's just 370. I said nearly. The first time I came here, by saying the most accurate manner possible, that's telling you. I don't know what you did. First of all, one person. This is why it's not. So I'm not. Did you solve it?
Yeah, we did have it on phone.
Okay, I'm gonna.
Well, my class hasn't started yet, so I'm going upstairs.
Yeah, we can do it now, actually. Let's just do it from scratch, according to your, your values. You guys, this might be a while, so you wanna, have you have a question? Which one, station 4? So no resistors, you, I mean, it has, it's irrelevant, right? But then you're artificially, you're not getting the same brightness that you would get.
Yeah, but you're just asking for longest lasting, and it lasts longer because there's less intensity.
Is that what argument? Talking about it. Okay, so for both of you, I'm gonna write down.
It wasn't mentioning brightness at all, so it's good to like dim this light afterwards.
Mm, I'm gonna try it out. Done? Thank you. So you measure negative. Okay. Bye. So when I did I found out zero volts. And on this graph, it's going to be 6 volts drop, and that's going to have an REQ of 5.5 or 5,500. Understand? Okay, so I got 0.0011. 0.0011 amps. And I wanted to find the voltage here, so I did that number multiplied by 2.2.
Is it
2,200. Okay, so 2. So here the voltage here is, okay, great. So that's 2.4, and that means this one is going to be 2.4 plus 3.11, 5.51 volts. All right, and now I can find the current here. So then 5.51. Sorry, no, actually, it's 9 minus 5.51 for the voltage here. And that's divided by, this would be the current, divided by 3,200. Okay, so that's going to be the current for this one here as well. So 0.001057, let's say, amps, multiplied by the voltage, which is 5.51. No, it's not, sorry, 5.51 divided by that number. Volts divided by 0.001057. Uh, 5.2 kilo ohm. It's a bit off, but is that what you did? You know, what's the difference between what I did and what you did?
Well, what I did is I solved it as if I had this value, like it was x.
Mm-hmm.
So then what I did was
So you
I
got this
basically tried to solve this one with this. I had my so my fifth, this plus this would be my RQ. So 3.3 thousand plus x.
Okay.
So since that's my RQ, my V 6 volts, then my I is going to be 6 volts divided
Oh,
by
sorry, we did 9 minus, but it was actually 6 minus. That's why
Oh,
our
okay.
number is off here. Right.
So instead of that, it's 6. And then
Yeah, that's what I got.
So then I had this.
Okay, so let me just keep following. So now you have 6 volts across this branch.
Mm-hmm.
Okay. Okay.
So then after that, to find the length of this one, the voltage is equal to I, which is this, times the resistance, which is X.
Okay.
And then this voltage is also equal to this voltage, right?
That is the voltage on this resistor, yeah.
So I did this. So I brought this one to this side. So then
And this is your, I think you made a mistake. This is the 5.15 and 2.3. Yeah.
because I did times for this.
Let me,
Yeah, thank you.
yeah. I'll look for it. It's not there? Okay. Thank you. Okay. If I have it, if I don't. Yes, this I have. Oh, this is good. Thank you. Thank you. Yes, please.
Ja, hier. Ja, da habe ich mich was gespart. Man kann hier Angst, der packt sich momentan. No, no, no. Ah, c'est cool. Oh, je suis arrivée dans ma chambre. J'ai vu mon exam. Like, I was in an exam.
Oh my
And
God.
I look at it, she's like,
Oh my God.
cool. Mais genre, j'ai couru. Je pense qu'elle a vu la panique, là. Moi, j'en file, je suis partie avec mon exam. Genre, je l'ai mis dans mon sac. Mais elle a rien fait quand elle sortait de la classe. Non. J'ai fait ça là. Je suis revenue genre 1 minute après. Il est là.
You made that? You did it? Well, if you don't have, then it's fine. Yeah.
We end up complexifying whatever we
Complexify. Yeah, of course. So you're right. I'm crazy. Yeah. I don't know. It wasn't. I don't know why I thought that. I thought I had an appointment, but I didn't. You want to meet now, Alina? Grab a chair. Actually, we can go sit there. We can go sit over there. Okay. So, if I have a circuit, forget about this. I have a resistor. But as soon as there is a circuit with a resistor and a capacitor, RC circuit. Okay, that's what an RC circuit is. R for resistor, C for capacitor. Now, when you have an RC circuit, this capacitor now doesn't charge automatically. Because if there was no resistor, as soon as you turn on the switch, then you would charge the capacitor instantaneously. Okay, but because there's a resistor, now there's a time delay, and it takes some time for it to charge. If I were to look at the charge of my of my capacitor and time, the charge would go like this, right? Slowly goes up and it reaches the maximum at, when does it reach the maximum? Actually never, it never reaches the maximum, right? But it gets very close to it, never reaches because it's an exponential function, right? So like you basically do an asymptote here. Okay, so now there's this value here, this asymptote, so this theoretical value, we can call it Q max. And that can be measured by using P multiplied by P. So this is going to have a capacitance, and this is going to have a voltage, right? And so when this is full, when this capacitor is full, so this is going to slowly start to go this way, and it's going to fill up, fill up, fill up, fill up, fill up. It's like a canister of water, right? So it's going to fill up until it can't fill up anymore. When this is full, right, this capacitor is going to have the exact same voltage as your battery. Okay, so if this is 12 volts, then this is going to be 12 volts. Okay, and if you have something that's pushing here with 12 volts potential, and this is pushing back with 12 volts potential, what's the current when 12 volts are pushing with 12 volts? It's pushing in both ways. Yeah, but it's just this one is the one that's going to get opposed by the battery. Okay, so this is going to push here, this is going to push here. So that if everyone's pushing the same way, then nothing's moving. That means when the capacitor is full, it's full, current is equal to zero, right? Because no one can go anywhere. Okay? The positive charges are trying to go there, but the positive charges are all here and they're trying to go there. So they clash. So there's no current. So if you were to look at now the current, right? So the current in this circuit starts off at a number, maximum, and then it eventually comes down to here, and then it becomes zero. The current becomes zero. Okay? That's what happens when you're charged. That's what happens when you're charged. Now, these charges are never going to want to go here as long as this battery is here. So how could you make this charge? Well, you have to remove the battery. Okay? So if you remove the battery by a switch or anything like that, now we can, let's say we remove this battery and we replace it with a straight wire. So now the circuit's going to look like this. Now, nothing is pushing against the capacitor. So this capacitor can allow a charge to go this way, right? And it's going to create a current through this resistor. Yeah, but now it's going to go in one way or the other, but because this is all the pluses here, so this is all plus here, okay? And it's going to be minus, minus, minus. And because of that, then the pluses are going to be the ones by convention, that's what we say. Okay, so now you have your charge moving in this way. So that means your current before, this is why you were charging. Now your current is going to start at a maximum, and as you use up this charge, the current is going to slow down again. So in fact, what's going to happen is it's going to do the same thing. It's going to start off, current is going to be really high at the beginning, and it's slowly going to come to stop. And the charge as well. Now the charge, it started off at its maximum, and it's going to slowly die off, right? And also the voltage, because remember, this 12 volts, gave all of its voltage here, so this has 12 volts to begin with. So now, the voltage of this capacitor is also going to be, okay? And this here, this initial was 12 volts. This initial here was Q max. This initial here was I initial. Okay, so you can calculate all these with formulas. So this one is going to be I P I naught multiplied by E minus P over R. This one is Q max, right? Q max multiplied by P over R. P as a function of time is going to be equal to V max multiplied by power. Okay? Okay, so you have the total battery here. Let's say it's 6 volts. Let's call one, say that's 1,000 ohms. Two, we're gonna say 2,000 ohms. Three, we're gonna say 4,000. So just do one. So 1 ohm, 2 ohm, 4 ohm. Okay. And so we're trying to find out what this unknown one is here. And so what we're going to do is we're going to take a multimeter or a voltmeter and measure the voltage across these two points. That's the weak point bridge. It looks like a bridge, right? Right. So if I have that bridge, right, I can figure out what my unknown is. So let's say that let's pretend that this is the measurement here. We're going to call that V drop. That value here, let's say it's volt. You have to take your machine and do it. In the exam, I'll tell you this number. Okay, so I'll tell you that this is called V drop, and that's the voltage difference between this point and this point. Right? So then, okay, so if that's the case, my V drop is going to be, let's say, I'm going to just make up a number. I don't really know if it's going to work. Let's say it's 2.5 volts. The difference between here and here. Okay. It's going to work. I'm going to make a smaller number. I don't want to risk it. Okay, so now, this, if you ignore this voltmeter, this here is in parallel with it, right? And these two are in series. So I can do 1 plus 3 to give me my equivalent here. So 1 plus 4 ohms is going to be 5 ohms. So this here is going to have 5 ohms here. And this we don't really know. Okay? And we can figure out the current going through this side here. So if we figure out the current going through that side, it's going to be 6 volts divided by 5 ohms. It's going to be this number, 1.2. That's the current going through 1 and 2 because they're in series. Right. That means I can figure out the voltage here and the voltage here because I have the current. So the current, the voltage for 1, so V1 is going to be equal to my current, 1.2 amps, multiplied by my resistance, which is 1 ohm, and that's going to give me 1.2 volts. That's my V drop for 1. Let's find it for 3 now. So V3 is going to be equal to 1.2 amps, the same current because we're in series, right? Multiplied by 4 ohms. That's going to be equal to 4.8. So there's a voltage drop of 1.2 volts here. And at this point, there's still 4.8 volts left to go. That means this point here is 4.8 volts. That's the potential here. And I told you that the difference is 1.5. Actually, I lied. That's my number is still too high. That's only 0.5. Okay. So let's say my dimension. That means that this point here is 0.5 volts higher than this. Right? So here it's going to be 5.3, I get 5.3 volts. Okay, and because I have the voltage here, I can use it to find my voltage drop here. So it's, again, this is 6 volts here, 0 volts here, so that means there's 0.7 volts up here. And with that, I can find the current in R2. Okay, let's do that. Current in R2 is equal to the voltage, which is 0.7 volts, divided by the resistance, and 2 is resistance, 2 ohms. Therefore, and 0.35. That's the current to this. But what can you say to me about 2 and 4? They are in series, so it's going to be the same current for this one. All right, so now we're almost done now because we have to find the resistance R4. And we have its voltage, it's 5.3. 5.3 volts divided by the current. That's going to And a circular which ball? So if a ball burns out, that means it has a resistance of infinity. Okay, no current can go through it anymore. Okay, so if no current comes out of the battery and needs to go there, it has to pass by A. So if it has to pass by A, but it can't because A is burnt, then the current cannot reach any of the other one. That's what it is. Yeah. Mr. Rock? Yeah. So I don't remember the numbers. Let's just say you were in my room when you had 3 lights or 4 lights? 3. Okay. So what it was okay. If you measured it, this one would have been something like 3 volts. The numbers are not going to be perfect. These ones are going to be like 3 volts, right? And each of these are going to be the same, but the brightness is different from this one. So if they all have the same voltage, but these ones are less bright, that means that the current going through them is smaller. And the only reason that the current can be smaller is if the current was split, right? So this one, the current was split, and this one has a full current. That's how you know it's power. Exactly for all of them. Yep. What's that? I can't remember the brightness of light bulb in the bulb. That. Ah, okay, because the question is asking you for brightness. Brightness is power. Yeah. Power is equal to I squared. Just you have to measure the current, and or in fact, you can do it the other way. P is equal to I times V. And so you can measure the current, measure the voltage like you did. You measure the voltage, and if you had measured the current, you could have multiplied the Q and got the resistance of the light bulb. So you have to undo the light bulb, measure the resistance of the light bulb, and then you can use that here. You have to practice. You have to measure. Good. Okay. Can I keep this?